So, welcoming all to this session on a webinar on how long would an EV battery last. So, this webinar is being delivered by Dr. Rutuj Deshpande. I'm getting an echo from somewhere. So, some basic rules before we start. Everyone should be on mute. Let me give you a brief intro about Dr. Rutuj. He is a battery scientist currently working as Deputy General Manager in Sterling and Wilson Private Limited, Pune. He is heading a team to design grid scale energy storage solution. And he recently has returned to India and joined SWPL. Rutuj also worked as lead battery engineer with Ford Motor Company in Michigan, where he was involved in designing automotive traction batteries for more than 15 vehicle programs, including electric F-150, Ford Mach-E, Ford Fusion Hybrid, plug-in hybrid, etc. Additionally, he is also a visiting faculty in Department of Chemical Engineering and Material Science at Wayne State University, Detroit. He has received his PhD in Chemical and Materials Engineering from University of Kentucky and performed postdoctoral research at prestigious Lawrence Berkeley National Laboratory with lithium-ion batteries being his primary area of research. Rutuj has authored 12 journal papers, 11 patents or patent application trade secrets in last 12 years of his battery research. Rutuj's research on battery degradation modeling is highly recognized in research community, totaling more than 1100 citations till now, and various international forums with awards such as Graduate Excellence in Material Science, Diamond Award by American Ceramic Society, Person with Extraordinary Abilities by USCIS, High Tech, High Demand designation for critical role in area for Ford's strategic priorities, Ford Recognition Award 6 times from Ford Motor Company, etc. Rutuj is reviewer for several well-known scientific journals, including Proceedings of National Academy of Sciences, Journal of Electrochemical Society, and Journal of Power Sources, etc. So I'm handing over to Rutuj now, and I guess we can start, Rutuj.
Hello. Hi everybody. Can you see my screen or not? Is my screen visible?
Yes.
Okay. For everybody for thanks Device Electronics for giving me this opportunity to present some of my work or some of my perspectives on battery degradation and battery life. And I would also like to thank everybody who's attending the seminar, taking out their precious time. First of all, with the COVID stuff, I hope everybody is staying safe, staying at home, and staying healthy. Uh, Coming back to the topic, how long would an EV battery last? That's a question that has been asked to me frequently for last 12 years, and I'm trying to answer it with exploration of physics, with the different aspects of physics in a cell, in an electrode, at the atomic level, at the cell level, or at the pack level. To give you my background, I'm currently working as a Deputy General Manager at Sterling and Wilson's Private Limited in Pune. I'm also adjunct faculty in chemical engineering at Wayne State University in Detroit. I'll briefly tell you introduce my background. I did my undergrad from UDCT or ICT in Mumbai. in chemical engineering. Thereafter, I joined University of Kentucky, where I did my PhD in chemical engineering with the focus as lithium-ion batteries, specifically degradation of batteries. My PhD was funded by General Motors. Thereafter, I could join the prestigious Lawrence Berkeley National Lab as a postdoc. Again, the research focus was lithium-ion batteries. After spending about 1.5 years there, I came back to Michigan and joined Ford Motor Company as a lead battery scientist, um, and worked on lithium-ion batteries for automotive applications. So various electric, hybrid, and plug-in hybrid vehicle programs. I was involved in designing of batteries, selecting the cells, selecting designing the controls, etc. I also joined as a adjunct faculty in Wayne State when I was in Detroit. And then I recently moved back to India and joined Sterling and Wilson, where I'm currently working as a deputy general manager. Here I work on large-scale energy storage solutions, specifically for grid application. As Durvankur mentioned, I have about 12 publications which are very well cited. Yeah, I recognized in the research community about 11 patents or patent applications, and there are more than 1150 citations in last 12 years to these papers. Okay, coming back to vehicle electrification, as we know, it's a buzzing word nowadays, and there is all over the world there is an increase in or there is a tendency to electrify vehicles or buy new electrified vehicles. There is a famous quote by a famous scientist, and he said, "I believe that ultimately electric motors will be universally used for trucking in all the large cities." He said, "I'm convinced that it will not be long before all the trucking in New York will be electric." Some of you might have guessed who this scientist is. Just to tell, is Thomas Edison. It's not a very recent quote, but it's in 1914. It was published in 1914. So we have been struggling, or we have been dreaming of electrification for about 100 years now. In fact, there were electric cars 100 years ago. The fact is, in 1900, about 38% of US automobiles were electric. People preferred electric vehicles at the time because there is no pollution. There is no cranking was required like the gasoline vehicles used to, and there was lesser noise in electric vehicles than gasoline vehicles. And now we are coming back to electrification again. So the question is, why electric vehicles lost the market in the early 1900s, and why are we seeing more and more EVs today? Both the answer to both the questions lies in batteries or battery technology. In early 1900s, the batteries could not keep up with the fast-moving gasoline vehicles, whereas now we have better batteries to provide the power required for the vehicles. Then among batteries, why lithium-ion batteries? Probably most of you know, lithium-ion batteries have highest energy density among all the available commercial batteries or commercial chemistries. Um, uh, for example, lead has about 50 to 100 watt hours per liter, whereas lithium-ion batteries have around 400 to 600 watt hours per liter. Again, this data is little old. Now the volumetric energy density at the cell level has gone up to 600 or more than 600 watt hours per liter in some cases, depending upon the geometry. High volumetric energy density, high volumetric and gravimetric power density. Power is what you would need to propel the vehicle, so to have higher acceleration or run the vehicle at higher speeds. Of course, you want long shelf life and long cycle life. So you can charge and discharge every day for so many years without really losing the capacity. So lithium ion batteries are best among the available technologies. There are new technologies coming up with higher energy densities, but they are still in research phase. Now, probably some of you or many of you know how lithium ion batteries work, but I just wanted to go briefly through it. Again, uh, when we see cylindrical or pouch or prismatic cells, we have basically layers of positive and negative electrodes and separators in between in these electrodes rolled together in a jelly roll form or stacked in the stacked format. But basically, any cell or any battery has two electrodes, positive electrode and a negative electrode, and they are separated by electrolyte. Again, this diagram is not to the scale, but just an illustration. Um, so in lithium ion batteries, we have lithium ions stored in one of the electrodes, and then as soon as lithium ions basically move from one electrode to the other electrode, and then electrons take the external circuit, and that's how we get electricity outside. So the amount of lithium that can be moved from one electrode to the other electrode would tell you how much is the energy density, or would tell you how many electrons you can take out for your application. That's basically the capacity of your battery. Typically, the negative electrodes are graphite based, either natural graphite or artificial graphite. The alternatives are silicon or LTO, lithium titanate, um, in certain cases. Typically the positive electrodes are LFP, lithium iron phosphate, NMC, or LMO, etc. So again, lithium iron phosphate or NMC, all of these are lithium ion batteries because ions are carrier of current in the electrolyte. So I see a lot of people saying LFP is different than NMC, but all of them are lithium ion batteries to the fundamentals. Okay, so coming to battery degradation, now we can basically look at it in a simple using a simple analogy. Battery, if we assume that these two tanks are like battery electrodes, so when we charge, we push water from one electrode to the other, or one tank to the other tank. So the lower tank to the higher tank, and when we discharge, we allow the water come back to the lower tank. Similarly, in lithium ion batteries, we push lithium from positive electrode to the negative electrode when we charge the battery, whereas when we discharge the battery, the lithium comes back to the positive electrode from the negative electrode. The only problem is this system is not leak proof, but it is leaky system. So that means, for example, in this analogy, the tank, we are losing water somewhere. So now each time we are cycling the water, there is small amount of water being leaked out, and we will lose that water. That means the capacity of your tank, total capacity of tank is getting reduced. Similarly, in lithium-ion batteries, the capacity of batteries would be reduced over time. For example, this plot shows there is capacity retention and years. So you start with 100% capacity, and then as you use the battery, as you cycle the battery or store the battery, there is some amount of lithium being lost. It's not recyclable anymore. It's basically leaked out, and then you would get less and less capacity out over the years. Now, what it means to an EV company. Basically, if you start your vehicle at 150 kilometer and you label the vehicle as the 150 kilometer electric vehicle, in 10 years, probably it will come down to 100 or 112, depending upon how badly your battery degrades. So your target was 150 kilometers, but your user would end up driving the vehicle only 112 kilometers on full charge at the end of 10 years. So that is basically under performance. That's not good for any OEM. The second way to size it would be you target 150 kilometers for end of life, and then you have to oversize the battery to 200 kilometers. So you need much bigger battery now to start with, and your customer will get all the benefits. He will get 150 kilometers, but you are paying for the benefits by oversizing the battery. And there is third option that you just sell the vehicle and don't care about it once you sell it. Hopefully, we don't have any EV manufacturers like that here. Now, to know how long your electric vehicle battery is going to last, you would look at a cell spec sheet. Typically, a cell spec sheet that you'll receive from a manufacturer will tell you two things. One is cycle life of so many cycles for certain C rate, so 1C charge discharge for whatever 80% retention. And they may tell you about the storage life, that if you store the battery at 25 degrees Celsius, you may the battery may last for 10 years. But the question is, if you have these specification, does that mean every battery that you have, or every battery that you will put in your vehicle would basically last for 2000 cycles or would last for 10 years? It may not be true. In reality, cell life is highly dependent on the usage pattern. So if your user is mildly using your cells, you may get certain degradation. If your user is little harsher or moderately using the cells, you may get other degradation pattern. Whereas if your user is really harsh, then your cells may last only so much. So you would get much faster degradation in that case. So same cell, even though they have same specs, their life would be highly dependent on the usage pattern. So what are the parameters that really affect the battery life? Of course, duration of usage, as we talked about. Then temperature of operation. If what temperature condition is the cell or the battery seeing when we are operating it? One factor is the ambient temperature. Second factor is the battery itself, the heat generation and heat rejection of the battery. Then total throughput, how many times you are charging and discharging, so similar to number of cycles. Then cell design, is it a power cell or energy cell, and how you are using it. Then depth of discharge, are you using full depth of discharge of 100%, 80%, 90%, or 50%? Then rate of charge or discharge, is it 1C, 2C, that the rate you are using for that particular cell design? What is the upper state of charge? How much is the non-uniformity within the cell? Does your cooling system basically rejects heat non-uniformly? And external pressure, especially in pouch and prismatic case, what's the external pressure you have on the cells when you make a battery pack? That's on cell level. And then you have battery pack where you put lot of cells together in series and in parallel or in parallel. Now, in battery pack, there are additional factors such as cell to cell variation. Each cell is not the same. There are manufacturing differences even within a batch of cells. Then there could be non-uniformity of temperature within the pack, and there could be things like cell to cell imbalance playing some role in the battery pack. So all of these factors would tell how your battery is going to perform, especially the life of the batteries or degradation of the battery would be seen over the usage. So we will be mostly focusing on these are so many factors, and we cannot deal with all of them in one webinar, but we'll just go through some of them briefly. One of them would be temperature of operation. The other would be depth of discharge and rate of charge and discharge. How they are affecting at the physics level in a battery. So typically we use a mathematical model. We have some data. We use that data to generate a mathematical equation, and then we use that equation to predict certain aspects of any system for that matter over life. How would it perform over life? this exercise of mathematical modeling is similar to what we used to the connecting the dots exercise when we were kids. Um, the only problem is in this particular case of life modeling, we are given only two data points: cycle life at some rates, and storage life at certain condition. So the data provided is very minimal, and we are expected to develop models which can really draw this elephant, uh, not just the elephant, but we need to predict the behavior of the elephant over time. So there is a data malnutrition in this particular field. That's where the models or the physics base of the model becomes very important. Uh, in the durability, so we are again talking about how long the battery lasts. So durability of the battery. In the durability literature, they commonly use a bathtub curve. So something like this. So this is time axis and this is kind of failure rate. So initially there are failures. These are infant failures and early failures. These do not typically come to the application engineer. These will be at the manufacturing side. The second would be the random failures or instantaneous failures. So things going wrong randomly. Typically for batteries, this number is very small. It's around 1 in 10 million or less than that, depending upon who's the manufacturer is. But if you are taking cells from good manufacturer, the random failures are really low. And then the third part is wear out failure, which is what the degradation is. So batteries gradually degrade over time, and then there is a distribution. So all the cells in a battery, basically in the durability literature, people use bathtub curve. Give me a second. Yeah. Basically, this is time axis and there are failure rates. Initially there are failures which are infant failures. These typically happen at the manufacturing locations. Then there are failures which are random failures. They are occurring throughout the life randomly. But for a good manufacturer, the random failure rates is low. For lithium-ion batteries, this rate is less than 1 in 10 million cells. And then there is something called wear out failures, which is basically degradation of batteries over time. Again, the wear out failures in a pack would not be same for each individual cell. There would be a distribution of wear out. So there would be a mean capacity loss, but then other mean capacity loss, and then some cells would see higher capacity loss and some cells would see lesser capacity loss. So our focus on this particular webinar is again wear out failures, wear out mechanisms for lithium-ion batteries. So they can be classified in two major categories. One is two major mechanisms. One is side reaction. So there are side reactions happening within the cell, which basically eat away the lithium inventory. It also results in gas generation, pressure buildup, or metal ion dissolution, resistance increase. So all these side reactions. And then second part is mechanical degradation, where the electrode particles or the SEI layer or the electrode laminates degrade due to electrode expansion and contraction. So we will look into all of these in the coming. Now again we have a cell, and then cell is made up of electrodes which are bundled together. So we see a positive electrode, negative electrode, and they are separated by electrolyte. Typically, the electrolyte solution is lithium iron phosphate, so dissolved in carbonate. So ethyl carbonate, diethyl carbonate, dimethyl carbonate. Now the problem is all of these carbonates or any solvent for that matter have a particular stability window. So they are stable in a particular voltage window. For example, these carbonates are stable between 1.5 to 4.3 at room temperature at storage conditions. The problem is our negative electrode has a potential of less than 1.5 it has average potential of 0.85 millivolts, whereas the positive electrode has a potential anywhere from 3 volts to 4.3 volts. So basically the electrolytes are not at all stable on the negative electrode surface, and in some cases they are not stable in the on the positive electrode surface as well. So comparing LFP versus NMC, NMC has a higher voltage. The positive electrode voltage is even higher than the LFP electrode. So LFP is much more stable than NMC because the LFP voltage is 3.7 volts on the positive electrode, whereas NMC can go up to 4.1, 4.2, 4.3 volts. The result is the electrolytes, which are carbonates, are not stable, and they decompose on the electrode surface. So as soon as they see some electrode surface, they react and they form some inorganic compounds such as lithium carbonate, or they may form compounds such as gases such as ethylene or carbon dioxide. So various reactions happen. These are side reactions or unwanted reactions. The result of these reactions is basically the electrode particle, which is surrounded by the electrolyte. You would see as soon as you form this cell, there is a layer of compounds or reduction products that are forming around the electrode particle. This layer is called solid electrolyte interface, or SEI. So this is similar to oxidation of metals when they are in air. So there is an oxidation layer on, let's say, iron or copper if you just put it in normal air. So these are similar products which basically form a layer. Now once a layer is formed, they basically reduce the rate of reaction because there is the distance between, so they kind of form a passivating layer. So the electrolyte is not in direct contact with the electrode anymore. So they reduce the rate of reactions, but the rate of reactions is not totally stopped. So these reactions basically continue over the life of the cell, and the thickness of this layer gradually increase over time. So what happens is, as these reactions are happening, more and more lithium is being confused. So this is the leak that we were talking about in the previous example. So these reactions are acting like leak, and they are basically eating away all the lithium from your system. So the solid electrolyte interface layers, this SEI layer tend to grow over the age of the cell continuously, whether you're storing or where we are using the cell. So there is a degradation over time. Now the rate of these reactions is temperature dependent, like any other reactions. So higher the temperature, higher is the rate of reaction, and typically they follow something called Arrhenius behavior. But what it means is you will have much higher degradation at 45 degrees Celsius than 25 degrees Celsius, and much higher at 60 degrees Celsius than 25 degrees Celsius. Whereas you will have lower degradation at 0 degrees Celsius when you just store the cell. Again, these are all example numbers. They may not apply to your particular cell. But now in real life, when we are designing our cars or vehicles, there is a variation of temperature throughout the life. For example, this is the blue curve is Phoenix temperature in USA throughout. So throughout year and then 10 years. So it's repeated over 10 years. And orange one is a temperature of ambient temperature in Detroit. Now, if you just store a cell, this particular cell, in Phoenix or in Detroit, you will see that you will have different degradation. So Detroit one will have much lesser degradation, whereas Phoenix one will have much higher degradation because Phoenix has higher average temperature. And in this degradation pattern, you will see that there are waves. These waves are being formed because of variation in temperature. Now, the same principles would apply to any designer who is designing here in India. We'll have to look at what is the ambient temperature change over the year for that particular location where your user is going to use the vehicle. Again, this is just ambient temperature, and the assumption is the cell is following the ambient temperature exactly. Whereas in real life, your cell would have additional heat generation when you're using it. It may have longer thermal constant, so it may take long to cool down and stuff. So cell temperature could be very different than the ambient temperature. So you'll have to look at the cell temperature rather than the ambient temperature. The important aspect of this understanding is that you will get different life when you are using your cells at different temperature conditions, and this could be used to basically find out what's the temperature limit that you would want for your system when you are designing your thermal management system. Basically how long you want your battery to last and what kind of temperature could it see over the life of the cell. So we talked about the ambient temperature, but there is second aspect, which is what kind of speeds your vehicle you want to use and what it means to the battery. So you can take a usage profile and find out what's the power requirement from the battery, what's the current delivery from the battery, and based on your thermal system, you can look at what's the temperature that your battery will see over time. So this is the plot on right is basically temperature for this particular cycle. And the idea is you design your cooling system, whether it's air cooled or liquid cooled, such that you can basically remain below a certain temperature, let's say 45, 55, whatever you choose, the maximum temperature you would like. Your cooling system should basically keep your cells below that temperature when you are using it, and that can basically prolong your life. So basically how management needs to understand what's the temperature limit for meeting your life requirement, and then what's the size of your cooling system to keep it within the certain limits. Next part is battery cycling. So we talked about battery storage, what is happening during storage, but second part is battery cycling. Again, to recap, lithium-ion batteries have lithium ions which are being transported from one electrode to the second electrode continuously as we charge and discharge the cell. So again, lithium-ion batteries are intercalation batteries, or the electrodes are intercalation electrodes. What it means is lithium ions will be diffusing inside the particles of your electrode. Now, whenever a host particle gets an additional lithium atom, the thing that will happen is whenever you lithiate your electrodes, so assume that these are electrode particles, these circles, and these are lithium ions, and when you start intercalation, you will see that your particles are expanding, and when you de-intercalate, your particles are contracting. The color change is also there in certain cases, but that's not of reference here. So as we charge and discharge our cell, lithium ions basically go inside the electrode particles. The electrode particles may expand, and when you de-intercalate from those particles, your electrode particles will contract back. For example, graphite electrode will see about 10% expansion on complete lithium. Whereas if you want to use silicon as your electrode, for your information, silicon has much higher energy density than graphite. But the problem with silicon is it has 300% expansion. So your cell may be much bigger when you charge the cell than when you discharge the cell. So there is this continuous expansion and contraction happening within the electrodes, and this is called electrode breathing. Now there are several effects that are happening as a result of this electrode breathing. We'll go through some of them here. So the first effect that happens is, remember we talked about electrode particle, and there is a SEI layer around the electrode particle. Again, this SEI layer is typically, so yeah, going back to our electrodes. So remember, our electrodes are surrounded by or have a coating layer around them of SEI, solid electrolyte interface. Now, when your electrode particle expands, like what we showed in the previous image, first thing that will happen is there would be a lot of stress generated on this coating layer. Basically, this coating is not expanding like your inner particle is, and this coating may break. So as soon as the coating layer breaks, there is much more electrode surface exposed to the electrolyte. So electrolyte basically seeps in through all these cracks and forms performs more side reactions. So there are more side reactions happening on these exposed surfaces. So this more side reaction will result in more capacity loss. That's why we typically see more capacity loss when we are cycling than we are storing it, and even if we are cycling at low rates. So this is just an expansion contraction effect. We can of course model it. I don't want to go into details of the model, but you can basically combine the diffusion equation with the stress equilibrium and find out what's the stress that this particular SEI layer would experience when your electrode is expanding, and what it means to the capacity loss. It turns out that we could find that the capacity loss is actually proportional to square of depth of discharge over the length of SEI. So this equation is very important, and we could patent it. There was a publication around it too. It is important because now we can predict how many cycles a cell can do for various depth of discharges, even if we don't have data. Remember, we have scanty data, we have very limited data of charging discharging, and we still need to understand how our cell will perform in a given situation. So for example, in this particular case, we had only 2 data points, the yellow circles. We used only 2 data points, and then this is the red circles are the experimental points, and then blue are the model estimation. But we see until at least 20% depth of discharge, we could predict it very accurately based on a physics-based equation about number of cycles to failure for a given depth of discharge. Now, why is it important? Because depending upon the application, whether it's a full hybrid, whether it's a plug-in hybrid or a battery electric vehicle, BEV, or pure electric vehicle, we may need to, our battery may need to undergo different number of cycles. Say, for example, the US ABC, the US Advanced Battery Consortium, has a target cycle number for FHEV is 300,000 cycles, whereas for PHEV it's about 5,000 cycles in the charge depletion mode and 300,000 cycles in the charge sustain mode, and for BEV it's 1,000 cycles. Again, this is long range BEV. So we need to know what's the DOD that we can use for meeting particular number of cycles. And that's why this equation become very critical, and we could and we patented it at Ford. Going to the second effect of cycling, typically this second effect you would see it when you have large C rates of operation. So you are charging and discharging at relatively larger C rates. Again, the large is very subjective term. For example, for power cell, even 2C, 3C may not be large C rates. For an energy cell, even 0.5C or 1C could be a large C rate. So it's a cell design specific term, but we will have to look at C rate for large C rate for that particular design. What people found is when they try to cycle the cells at higher C rates, they will see the electrode particles cracking inside. So the electrodes are made up of these particles which will break over time, and typically they will see it at higher rates and lower temperatures where electrode particles will totally pulverize. So we wanted to understand why would it happen. Going back to physics, basically when we are charging and discharging, again we are lithiating from the outer surface. So as we lithiate, there would be higher concentration of, if we assume that this yellow is the lithium concentration, there would be higher concentration of lithium atoms outside, and these lithium atoms would gradually diffuse in towards the center as you lithiate. So there would be, initially there is no concentration, then there would be a concentration gradient. What it means is there is higher concentration outside and lower concentration inside, and then the concentration gradient would be different at different stages of usage. Also, it will depend on the diffusion coefficient of your electrode and stuff. Now, why these concentration gradients are important? Because these concentration gradients will create stress. What kind of stress? It's called diffusion-induced stress. So diffusion-induced stress are very similar to thermal stresses. Probably many of you know thermal stresses. If you have metal plate and if you heat it from one side, if you have higher temperature of plate on one side than the other side, so you have to heat it quickly, what you will see is the metal plate bends. That's because the side which is warmer expands more, whereas the side which is not yet warm would not expand as much. So to maintain the continuity, the metal, there would be thermal stresses happen, and then the metal plate will bend over time. And then you can use Hooke's law to calculate the stresses in thermal expansion. Similar thing is happening here in diffusion case. So as your lithium atoms are diffusing in your electrode, there is higher concentration of lithium atoms on one side of the electrode, whereas there is lower side on the other side. In this particular case, there is lower concentration at the center and higher concentration at the surface. So the surface part wants to expand more, whereas the inner part, which doesn't have enough lithium concentration, does not want to expand at all. But to maintain the continuity of surface, there would be a compression on the outer surface, and there would be a tension on the inner surface. So there are these stresses happening, and these are diffusion-induced stresses. And then you can calculate how much would be the diffusion-induced stress when you are charging and discharging your battery at a particular rate. Again, higher the rate, higher would be these stresses. Now you can basically calculate the diffusion-induced stress at different times. For example, this is 0.01 normalized time, and this is 0.4 normalized time. So at different location within the electrode particle, you would have different stresses. So there are positive stresses, which are tension, and there are negative stresses, which are compression on some part of the electrode particle. Now, each time you are charging and discharging your cell, each of your electrode particle is seeing some positive and negative stress. So there are tension and compression cycles that it is experiencing. And if you go to fatigue mechanics, every material can sustain certain fatigues, certain stress for so many number of cycles. So this is basically the number of cycles to failure for a given stress you can know from fatigue mechanics. So similar principles could be applied on electrode particles, and we can gradually know basically how the electrode particle, how much stress the electrode particle is suffering, and what it means to the particle. So higher rates, higher would be the stresses. Lower temperature, again diffusion becomes slower, and then the stresses become higher. So what's the implication of these stresses? So the electrode particles may gradually crack. Now there is this electrode particle, and then there are always some defects to start with on a particle. And as you are doing charging, discharging, these micro cracks will gradually grow. Now what happens is, whenever there is a crack, new electrode surface would be exposed to the electrolyte. So electrolyte can just seep in this crack, and it will react on the surface and then basically form new SEI or have more side reactions on this surface. So there is more loss. So it's this kind of degradation is called coupled chemical mechanical degradation. Remember, if there was only mechanical degradation, it may not be as bad. But if you have, since we have these chemical reactions which are eating away lithium from the from the system, it becomes more harmful. So you can use, say, classical Paresis law to understand what would be the crack growth in the electrode particles. And based on that, you can come up with some equation which will tell you how much would be a capacity loss if you're charging and discharging the cell at a particular rate of operation. So we could use this equation on a A123 data, and we could basically fit the data very well based on the physics again. So this is third type of degradation mechanism basically happening within the electrode particles. Now there are additional degradation mechanisms such as lithium plating. So if you're trying to charge your cells at really high rates, specifically when you're already close to fully charged, so your higher SOCs, higher state of charge, if you're trying to charge your cells at high rates, you may see that the lithium, rather than intercalating, it will just plate, it will just deposit on the electrode particles. And as soon as it deposits, it basically reacts. Hello. Devankur, can you hear me?
There was some noise. I don't know. You can continue now.
Okay. So yeah, so I was talking about lithium plating. So this typically happens when you're so those could be additional degradation mechanisms. The other could be cell swelling. So each time you're charging and discharging your electrode, the electrode particles are swelling. That means the entire electrode is swelling. That means the cell will swell, but cell will contract down. Maybe this cell expansion and contraction may not be as elastic as you would want. It could be a plastic expansion. Additionally, there are a lot of gases being generated, especially when you're using your cell at higher temperatures or higher currents near the high SOC ranges. So that's where you will see these cells ballooned up, especially pouch cells and prismatic cells, you will see more. Then there could be mechanisms such as non-uniformity in cooling within a cell or within a pack. Certain part of the cell or pack could be at higher temperatures, the other parts could be at lower temperatures, and there is non-uniformity in degradation because of current distributions. At the pack level, you may see that there is a mean degradation or average degradation you have, but there is a distribution around the average distribution. So you have to understand what is the distribution, because in a pack, if all the cells are in series, then the cell which is weakest or has least energy would decide the energy of the pack. So basically you need to understand the distribution. Again, the better quality of cells means lower distribution, so lower 3 sigmas around the mean. So all these factors could come into play depending upon your particular application. So in the end, we can basically develop a simple life model. For moderate operations, you just need to understand these 3 physics principles. One is the side reaction that are continuously happening. You have to basically put it in the mathematical equation. Then you have SEI cracking, which is continuously happening as your electrodes are expanding and contracting. And there is a particle fatigue, which will happen only at higher rates of operation. So your typical battery model would look like something like this. Your input would be either vehicle speed or power requirement from the battery. The temperature, this temperature could be just the ambient temperature, and then initial SOC. And then you will run your profiles for 1 year, 2 year, or 10 years, whatever your target life is, through an equivalent circuit model, which will basically tell you what's your state of charge, what's your voltage, what's your current from given speed or given power. And then you will use that to understand what kind of effect that current is having on SEI cracking, side reactions, or particle fatigue. And combining all of these, you will find out what's the new capacity or what's the new resistance in your cell. Again, resistance part I could not cover in this particular webinar, but we can calculate that. And then there is a feedback loop. So basically, whatever capacity degradation you have calculated would also affect your next time point equivalent circuit model. So or any thermal model for that matter. So there is a loop around it. So so the idea is your input would be speed and temperature, and your output would be capacity retention for different locations. For example, you can put different locations, temperature conditions, and usage conditions. So that's the big battery life model we can generate. And basically, this model will tell you how long your EV battery lasts. I won't be able to tell you right now. So again, coming back to the original question, how long would an EV battery last? Answer: it does depend. It depends on your quality of cells, the characteristic of your battery pack, and the usage profile. You're expecting what's the 90th percentile or 95th percentile or 99th percentile customer usage that you would expect, and based on that you can design your batteries. Can one estimate the life? Yes, definitely. If we follow the physics, we can definitely come up with simple equations that can tell you how long your battery is going to last. Again, principles of physics are universal; they are not going to change. And as long as you know the mathematics, which is language of physics, you should be able to predict or estimate the life of your battery. At last, I feel like any battery life modeler is like a astrologer, and we are trying to predict the things happening in life of this battery balloon. I think that's where I will stop. If you have any questions, you can go ahead. Thank you.